Hello and welcome to our last video notes of the AP Stats Year 6.5 Regression Slope Inference. Yes, we are going to be thinking about linear regressions and talking about running hypothesis tests, constructed confidence intervals, just like we did with proportions and difference in proportions, and just like we did with means and difference of means. So let's take a look at the context we'll be staring at for the front half of this particular video notes. So in many states, students are required to take high-stake math tests in order to graduate from high school. California used to have it, and then it got voted away for very good reasons. Hopefully it never comes back. And so there's also standardized tests, of course, for college admissions, like SATs and ACTs, although those are also kind of disappearing, thank God. And oftentimes, students report having a lot of anxiety about these tests along with other tests in their life. And so the question becomes does your test anxiety interfere with your ability to score on a math test? This particular psychologist selected 24 random students for a study. The psychologist interviews them before the math test, assessing their anxiety level on a scale of 1 to 10, 1 being low. And then they took the test, and then you can see there what their score is in terms of a percentage there. And all the data is there on the right. So before we jump in, I wanted to make mention of some things that you are expected to be able to do that harkens back all the way to Unit 1 and some stuff from this unit. So if you wanted to, you could pause and kind of dig in to make sure you can do each of these things here listed, which is create a scatter plot on your calculator, describe a scatter plot in context using the ideas of strength, direction, form, and outliers. Find a least squares regression line model on your calculator. Create and analyze a residual plot on your calculator. Explain the meaning of a that says the correction. It's supposed to say correlation coefficient and coefficient of determination. Correlation coefficient is R, and coefficient of determination is R squared. Let me fix that really quickly. Correlation coefficient. Interpret slope and intercept of your model in context. And then finally, find and interpret residuals. So if you're not sure about any of those, go back and find videos either from the Unit 1, or from this unit to make sure you can do these things. Some of these will come up immediately as we're working here. In fact, if you haven't done so already, you should type in these data values into your calculator before we proceed. Okay, so if you've done that, let's talk about what you would find out. So if you type in these calculators and run a regression line, which you should do, you're going to find that you have a weak negative association between these two variables. Its slope is negative 4.49, so it's saying that's basically on average your higher anxiety level means a lower math score. And its R squared is only 27.56%, okay? So that's pretty weak. And because it's weak, we might ask the question of is it that there really is an association between these two variables, or is it just due to sampling variability that we are seeing some sort of association, okay? You could pretty much throw random numbers into your X table and into your Y table, run a regression, and it'll pop out something at you, and it doesn't mean that there actually is an association. It could just be by chance alone. So that's what we want to know. Is it just by chance alone that we are seeing some semblance of a linear association between these things with this negative slope? So to figure that out, we're going to go ahead and perform an inference test for the true population slope. So if we were to actually poll every single person to ever take a math test and their anxiety level, what would that association's slope be? So let's get into it. First, we are going to state what we're doing here. Since it's a hypothesis test, here's where we want to state our hypotheses. So our hypotheses are formatted like this. H naught is going to be beta equals 0. And if you're like, what's beta? I'll explain in a moment. And our alternative is that beta is not equal to 0. And let's define what beta is, where beta is the true slope of the LSR model relating anxiety level to test score. So our null hypothesis is that the true slope between these things is 0, okay? If it was 0, then that would mean there really is no correlation between these things. You know, it's effectively drawing a horizontal line through all of your data. Just ultimately, there's no correlation going on there. Obviously, if all of your data landed perfectly on a horizontal line, it would have a slope of 0, but your regression, your correlation coefficient would be, your correlation would be very high. Like obviously you're predicting perfectly, but as we can see from our data here, that's not going to happen. We're not going to have all the same test scores here. So we got variability, which means that by paying attention to sort of what the slope is doing, that helps us out. And so the alternative is that b does not equal 0, okay? You can express your alternative as being less than or greater than if you have an inkling about like, oh, you know, I think it probably does this. I think as this increases, this other variable increases or decreases. That's my forethought. In this case, we're just gonna go with that like, no, like it's not a slope of 0. Obviously, we see what our statistic is up there for the slope, but we're not gonna let that sway us, okay? So we're basically testing, is the correlation between these things nothing? In other words, that's we just have a horizontal line that goes through them that does the best job at predicting, or is there a non-horizontal line that does a better job at predicting? So let's get into our plan now. So we're going to check off some conditions as we usually do. You notice there's a lot more bullet points than perhaps you're used to, and there's some new definitions we'll talk about. But I think you know what the first two conditions are going to be. It's those same ones we have gone through every single time. So take a moment, think about them. If you want to write them down, you can. So I also put in the name of the test we're doing here. Forgot to mention that earlier. So this is a t-test, okay? Because we're really thinking about, you know, a kind of a mean here. Slope is sort of a meanish value in terms of like average rate of change, right? So that's we're going to use a t-test for in this particular case. Not a z-test because it's not a proportion, and we don't know the true population standard deviation. And the first two things that we're going to check off, hopefully you thought of: randomization, the sample is given, it says that it's a random sample of 24, and independence. You know, you could sort of think about like, yeah, less than 10% of anyone who's ever taken a math test, that's one way to do it. If you were thinking more specific, like this math test, it seems like this is a very particular math test that this psychologist created. So I'm gonna just go with that the independence is assumed between the test takers. Like they're not cheating off of one another or like in some way influencing their anxiety levels, that can happen, obviously, but I'm going to assume that it didn't happen here. So let's get into the new conditions here. So we have one called the nearly normal residuals condition. The nearly normal residuals condition says that the residuals must be approximately normally distributed. So what does that mean? That means that we need to check that the residuals, okay, so not any of our x's or y's up here, but that when we run the regression, that the residuals are roughly normal. And we've done normality checks before with data, and the best way to do that is with a normal probability plot. So let's jump over to the calculator and check out how to remind ourselves how to find the residuals and then go ahead and graph them in a normal probability plot. So first what we're going to do is check out to see if our residuals are nearly normal. So the first thing you should have done is enter all the data into your lists 1 and 2, and you should have ran a linear regression on this for lists 1 and 2 to come up with your linear model, like so. We do that because when it does this linear regression calculation, it also calculates our residuals for us and stores them in that little list called resid. And that's what's going to help us out here. So if you haven't done that already, pause the video, do that. I'm continuing on though, because I've done the regression model already, which means my residuals are already plotted for me. I'm gonna go to plot number 1. I do not want to look at a residual plot yet. I want to look at the normal probability plot. That's the last one, press enter, for my residuals here. To find my residual list, recall that you hit second, and then you're gonna hit stat, and notice in light blue it says list. There's all your lists, so if you ever just want to enter them, and this is list 7 for me here, press enter, or I could just hit the number 7, and I'm gonna hit, oh, before I do that though, I'm gonna hit y equals to make sure, okay, I'm cleared out. Sometimes I have extra graphs in there, I liked having it not. So I'm gonna hit zoom 9, and there are my residuals along this, and as we can see that it looks roughly linear. So this one's a little bit maybe of a close to an outlier. If you were worried, you could box plot it to see if it actually is an outlier, but it doesn't seem to be too straight and far from that linear shape there, so I'm gonna keep it in. So as we saw, our residuals through a normal probability plot show a roughly linear sort of relationship there. So we're gonna go with, yes, checked off, these residuals are nearly normal. The next condition is the straight enough condition. Sounds very casual. And that's where we're gonna check that the association must be, as it says, straight enough or approximately linear. So you can do this by looking at just the scatter plot while graphing your linear regression line with it. But I prefer, because it is talking about sort of like, in other words, is a linear model appropriate? Okay, that's really what this is sort of checking for. I prefer to go to the residual plot. So let's go ahead and head on back over to the calculator and let's look at our residual plot to see what it's showing us. So now we need to see if a linear model seems appropriate here. So we're gonna go ahead and go back into our stat plots to create a residual plot. So going back into plot 1, and it's still on the normal probability plot from before. I'm gonna arrow down and I'm gonna select this very first type of graph, that is the residual plot. I do not want to plot the residuals against the residuals, okay? If you recall in a residual plot, the y's are your residuals, x's are your original x's. So in my case, that's list 1. So I'll hit second 1 to get the list 1 in there, and hit zoom 9 again to get us a stat plot for all of this. And I can see there that particular residual plot is not showing much of a pattern at all. It does not have a clear U shape or, upside down arch or something like that. It is in fact randomly scattered, and that means that it is a good fit for linear model that is linear is appropriate here. So we saw that our residual plot shows random scattered points there. So I noted that, and we can check off that straight enough condition. The last one is equal variance condition. So this is checking off that the variability of y must be approximately constant or equal for all values of x. How do we check that out? Well, that's another thing that we sort of talked about when we looked at residual plots, is that's making sure that the sort of scatter above and below is pretty well balanced all the way through. So let's go back to the calculator and I'll show you what I'm talking about. Let's just keep looking at this residual plot here, because what we're looking for is that there's sort of like equal spread as we move along here in our residuals from here, low x's to higher x's in this case. It does appear to be that way. What we're looking for is like a fanning. So if it turns out it's pretty tight in here, but then as we move along it fans out and widens, or vice versa, if it's like for lower scores, or sorry, lower anxiety levels, we have high variability, but then it tightens in as we get farther out. Those would be indications that perhaps our test cannot move forward as we'd like. But here, there doesn't seem to be that sort of fanning pattern at all in any of this. It seems like the bouncing back and forth is happening fairly randomly, and that's what we like to see here. So we're gonna go ahead and say that, yeah, we've got about equal variance in this scenario. So we checked it off. The residual plot shows about an equal variability above and below the x-axis, and I drew over here an example on the right side of a particularly bad example. So if you want to draw that as well to give you an idea and remind yourself of like what would break that condition, and something like this would, where it's tighter maybe for smaller x values, but then kind of fans out as it moves to the right, or vice versa. So if you see something like that, it turns out you can't use this test because it's not sort of equal variability in all of this. Perhaps there are subsets that you need to sort of break this up into and maybe run multiple tests. But we're not going to do that here because we saw pretty equal variability above and below. So now let's go ahead and get into our do step. So we're going to let the calculator do a lot of work for us here, but I did want to remind you of some formulas and some other calculator functions for you. And I need to introduce you to degrees of freedom. So t-tests have degrees of freedom, and we have them here as well. So let's note that degrees of freedom in this case is going to be our sample size minus 2. Because we have two different variables is sort of the layman's explanation here. When we were only dealing with one variable earlier, then it was just minus 1. Now we have two variables. When we were dealing with a difference of 2, it was wonky and weird, which we didn't really get into. So, but in this case, it's minus 2 because there's two variables. So in our case, we're dealing with 24 different test takers, which means our degrees of freedom is 22. Awesome. If we were going to do this by hand, the formula is exactly the same as it's always been in terms of structure. So we're doing a t-test with the degrees of freedom of 22. And the formula is always your observation minus the null value all over your standard error. Deviation, sorry, whoops, messed that up. Standard deviation of our sample here. And so in this particular case, if you ran the regression, then you already have it there in front of you. If you haven't run the regression, you should. You probably did if you were following along with the residual plots. But our slope in this case is negative 4.49. Our null value is that the slope is 0. You can see that up here at the top. And our standard deviation is, well, we would have to calculate that to try to figure it out. So there is a formula that we could follow and use and do it, but that's not as fun here. So in this particular case, we're not going to deal with this, okay? If we did know it, which I'll actually just tell you, if we were to actually do this, we would know it to be 1.551 through a formula that I'm not going to share with you because I'm going to show you the different ways, okay? But if we did know it already beforehand, then we would get a t-statistic of negative 2.89, about-ish there. So, again, you don't have to actually calculate this by hand, okay? I was showing you an example of if you did, for some reason, get some information about this, which maybe you would if they gave you some computer output information, you would know what the standard error here is in this case. But in this particular case, we didn't really know it. But I wanted to show you how you, if you know the t-statistic, how you can find your p-value moving forward. And then I'll also show you next how to just actually use your calculator to run the whole test to find your numbers. So I calculated the standard error for us off to the side. You didn't get to see what the formula is, which is totally understandable. But I'm doing that to sort of show you that if you were ever dealing with a problem where you knew your standard error and you weren't given sort of a list of data, how could you go about finding your different values? And in this case, we have the t-statistic and our degrees of freedom. What we don't have is the p-value. And so we want to jump in and think about how to find the p-value. If you don't remember, we can do that with our distribution list. So if you hit second and then vars, which you'll see the DSTR up below it, that's the distribution list, we are dealing with a t-CDF. We want to do a cumulative CDF function here. And so in this case, our t-value is negative. we're going to go ahead and calculate the left tail of this, okay? So it has in there -1 times 10 to the negative 90, or to the 99th power. You can leave it as that if you want. You can also hit a bunch of 9s if you'd like. And our upper is going to be -2.89, because that was the calculated t-value if we knew our standard error from all this. Our degrees of freedom is 22 from our values here. And then we're going to hit paste and hit enter, and there we get a p-value. But before you write that down and go, so my p-value is this. No, okay? P-value is actually not this value. We need to do something to this because of the way our alternative hypothesis is stated. Take a moment to think about it. If you need to pause, do it. So the true p-value is double this because this is only the left tail, okay? And we want to think about the two tails due to the fact our alternative just says not equal to. So I'm just going to go 2 times my answer here and get that my p-value is about 0.08584. Doesn't matter with the rounding there. So that's if you have a t-statistic, how you can find your p-value. So let's go ahead and run the test on the calculator. We've done kind of some of the work here, but I calculated that standard deviation, beforehand, and I didn't show you how to do that. So this is the way to sort of do this problem. So we're gonna go stats, and we're gonna go over to tests, and we're gonna arrow all the way down, or you can arrow up, and it'll end up at the bottom of the list. And we're gonna do here a lin-reg-t test. There's also a lin-reg-t interval, but we're gonna do a lin-reg-t test in this particular case. And so we're gonna hit enter. And what you can see is that they ask you for what are your explanatory and response variables. So I already have them there in list 1 and list 2. Frequency, just leave it as 1, don't mess with it. And we are testing here that beta is not equal to 0. That's the alternative hypothesis. They don't ask you about like a null because they assume always that it is 0. And we're not going to store the regression equation if we don't, it's not an important thing to do. And we're going to hit calculate. What you'll notice here is they give us the t-value, okay, which is what I calculated by hand, but you didn't know what the s value was earlier, so now you know what your t-value is without needing to know what s is. It also gives us our proportion in this particular case, and the degrees of freedom, 22 is what we were expecting. It also gives us the a and b value from our regression line, so it kind of calculates the linear regression model for you while also running the test, which is kind of cool. And then it has some other information, s, r squared. S is important for higher level stats, but we don't get into it in this particular class. So in the end, we get a p-value of 0.084. So in a situation like this, when you're given the data, you're going to enter the data, and you're going to go straight over to the calculator t-test. And all you need to report out is what are your degrees of freedom, what is your test statistic, what is your p-value. You don't have to do those by hand. Now, of course, if they give you more information, sometimes it does require doing a little bit by hand and using the tcdf function instead. But in this case, this is a scenario where since I have all my data already put into the calculator, I just go straight to the t-test. So now let's go ahead and finish up this front side by concluding. We're going to conclude in the exact same way, in the same structure, in the same sentence frame that we've been doing this whole time. So I start out with doing a comparison. Since p equals 0.0084 is less than alpha. We didn't actually set an alpha, if I'm looking up correctly and seeing the original problem here. So in this particular case, that's a small enough p-value that any reasonable alpha level I set will work out for us, but I'll just go with the old standard of 0.05. And on a test, you'll definitely be given the alpha level. So since that is smaller, we reject the null hypothesis. There is statistically significant evidence that there is a linear association between test score and anxiety level with a slope not equal to 0. That's how we're going to finish it out. That was really what we were testing out here, is that there's a linear association and it's not just a horizontal line, that there actually is something going on here. And the evidence seems to be pointing more towards that this is a negative slope, which we could collect more data and now maybe try to see like, yeah, is it actually a negative slope here? And figure out whether that gives us significant evidence or not as well. All right, so now let's move on over to the backside. So now for the backside, we're going to look at constructing a confidence interval for the true slope. So the situation this time around is a physics class. They were given 5 different heights to drop from, a total of 70 different paper helicopters, and they computed sort of a regression that compared how high they dropped it from to the time it was in the air, flight time. This time around, the raw data is not given to us. This time around, we have a computer output that looks pretty familiar, and given a bunch of different plots over here on the right side here. We got the original scatter plot, we've got the residual plot. Looks like that's a histogram of the residuals, and that appears to be the normal probability plot for the residuals there. So let's get into doing this. We're going to construct and interpret a 95% confidence interval. So to start out with, we state, what are we doing here? Well, we're not testing a hypothesis. What we're doing here is constructing an interval, because what we're hoping for is we want to estimate the true slope of the least squares regression line model relating drop height to flight time. Awesome. So that's what we're doing here. And now we're going to go ahead and plan. So this is going to be called a t-interval for slope. Just like before, it was a t-test for slope. This time, though, we're constructing an interval, so this is a t-interval. There's some info that I didn't really give in the context here, just because I kind of ran out of space and was going into it. So I'll get you started on your conditions here. We're going to say that randomization is assumed. As it turns out from the context, that students were randomly assigned which of the 5 heights they did. So they did, I think, just one helicopter dropped at one height, and they were just randomly assigned one of those 5 heights here. And then we're also going to assume that independence is okay. This is a scenario where it doesn't really make sense to say less than 10% of the population, because the population is like dropping helicopters, and you're not like polling from that, you know, like that's not a population you're polling from. The less than 10% is important when you're sort of sampling without replacement. Here, these are just individual trials, and so it's fair to assume that each trial is independent, because each helicopter, paper helicopter, is only being used once. They were randomly assigned, so it's fair to assume that. So those are the 2 normal ones and the ones that are a little bit trickier because I didn't give you the full context. However, you can definitely do the last 3. So they are the exact same as the other 3 that we did on the front side. And you might be thinking, well, hold on, I don't have the data in my calculator. I can't make all the fun things that you showed us on the front side. Well, that's why I gave you all these displays up here. So what you should do during this time is think about which of these displays help you check off the last 3 conditions. Make sure you write those out, okay? and come into class ready to talk with your neighbor and share with the whole class how you checked off each of those three conditions. So now let's get down to the do step. Just like I did on the front side, I will do some sort of formula showing for you and think about what gets plugged into what. But ultimately, we're going to jump to the calculator to help us finish it out. So the formula for this interval is exactly the same as it has always been, which is first we start with our observation. So like our sample gives us a slope that we'll call B. We'll start with that. Plus or minus our critical value with the degrees of freedom that we can calculate now that we know how to calculate degrees of freedom, times the standard error for our slope here. And so we actually know most of this stuff. One of them we're going to have to sort of, if we wanted to do this by hands, kind of compromise on, but we know most of this stuff. And again, you might be going, wait a minute, you didn't give us data. How am I supposed to know what these things are? That's where our computer information comes in handy here. Up here, we can see from this what is our particular observed slope from our regression line, as well as what is the standard error of our slope from our regression line. See if you can tell which one is which. So hopefully you said that we're looking at this column right here. Drop height is our explanatory variable, and that's the slope, the coefficient, and that is our standard error. What we don't really know is what is our T star value, our critical value here. You might be inclined to grab this, but no, do not. That is not representing our T star value at all. So do not grab that and think that it's going to work out for us, okay? So let's plug in what we do know and talk about things. So we do know that our B value is going to be 0.0057244. Plus or minus, we don't know the T star, but we do know that our degrees of freedom is going to be 68 because there were 70 total helicopters dropped, and 70 minus 2 is 68, times the standard error, which again up there in the table tells us is 0.00, lots of zeros, 2018. Awesome. So if we wanted to do all of this by hand, this is where we would need a t-table to try to figure out what this is. So let's go ahead and look at our t-table because our calculator is not going to be very helpful here. Just like with our t-test, it's going to request from us the list of our explanatory and response variable data values. We don't have that. Best we have is what's up here. And as I said, the T that you saw there is not the T that we're actually going to be using here at all. So how do we figure this out? We can go to the T table, okay? And here it is. It's been a while. We haven't looked at this in a long time. And we're looking at a 95% confidence level, which is right down here. So I'm going to look in this column up above it. What you might notice is that like, oh, I don't have 68 in my table. 68 is not part of it. So what do I do? Well, the only option is either to round up or round down. And what you'll notice is if you round down, you get a bigger T statistic, so that means a wider interval. Or if you round up, you get a smaller T critical value, which means a narrower interval. Which one do you think is a better call for the purposes of trying to do our estimating here? Hopefully you thought making it wider is a better call because that means that you're sort of covering your butts. If you go too narrow and it turns out like, oh no, it's supposed to be a bit wider, then you're still sort of encompassing that. You're kind of giving more wiggle room to yourself than you actually need, which is okay. And it's not by a ton. We'll actually see on the calculator how we could have calculated a more accurate T-star value here. But in this case, we're gonna go with a round down of 60, which puts me at a solid 2.0000 is my T statistic. So we're going to go in and finish this up here, 2.000 times 0.000218, which equals, in this case, 0.005724 plus or minus 0.004036. All right. Which you can rewrite. I'll do the math for you here just to help you out. 0.005328, comma 0.006128. This is an obnoxious problem. Apologies for how many zeros there are here. So there you go. So if you wanted to be slightly more accurate, and you'll notice that it is like we're still very accurate, let me show you on the calculator how you can find your t-star with a little more accuracy. So we just saw how we can use our t-table to come up with a more conservative interval. If you were interested in being a little more accurate, then you can find your t-star value more accurately using your calculator. So what we're going to do is we're going to go into our distribution menu. And this time around, we don't know t and want to find the area. Instead, we sort of kind of have an idea of our area, and we want to know what is the t associated with that. So we're going to go with inverse t. And what is the area? This is where actually the t-table is still helpful, because for a 95% confidence interval, if you look at that column and look all the way at the top, it tells you that the tail probability is not 5%, but 2.5%, because remember, we usually split the leftover 5% over the two tails. And then we can type in our degrees of freedom. 70 helicopters minus 2 gets us 68. And when I hit enter, this will tell me the more accurate t-star value, which is negative, positive, because we're doing plus or minus, doesn't matter, 1.995. We used 2. You can see that we are very close with what we used here. It seems like it's almost about halfway between the two values that were sort of provided for us. And this is a much better sort of more accurate value. So you could use this if you wanted to go back over to your paper and recalculate it using this. What you'll notice is that we are still accurate to several decimal places. I think 5 is what I recall. So you don't need to be that accurate. We'll still be okay. But I just wanted to show you that if you wanted this, you could do it. All right, so now at this point, we are going to go ahead and let you finish it off. You can make this conclusion. You have concluded intervals before in your life. I can give you a hint. We are 95% confident that ... And so I want you to write it out and be prepared to share in class your ideas of how to sort of talk about this. And we will see you in class for our last new activity of the year.